Quantum computing, the dawn of a new era. Did you know that a chip has managed to solve an equation that was once deemed impossible, and it did it in just 5 minutes? That chip is called Willow, and it's the latest groundbreaking creation from Google. At first glance, it looks just like any other chip, but its implications for the world of computing are massive. Imagine this. If that same equation were handed to one of the most powerful supercomputers on the planet, like the Frontier, it would take over 10 billion years to crack it. Yes, you heard that right, longer than the universe has been around. Today on AI Thunder, we're diving deep into what quantum computing really means, the incredible potential it holds, and the significant risks it poses for humanity. We're going to explore 2 important questions. How soon can we expect this technology to be in our hands? And do we really want that? Hey there, I'm Cyrus from AI Thunder, and I'm thrilled to take you on this journey, so buckle up. The quirky-looking machine you're seeing right now is a quantum computer, and I'll explain why it looks so unusual a bit later. Now, quantum technology aims to make an exponential leap in computer capacity by mimicking the principles of quantum physics. I know physics can seem daunting, but don't worry. I'm breaking it down in a way that's both simple and digestible. Quantum mechanics explains that electrons, protons, photons, the very building blocks of our universe, act quite differently compared to what we perceive in the everyday world. The dream of quantum computing seeks to transcend the limits of conventional computing. Our current chips rely on logical principles that reflect our visible reality, whereas quantum chips aim to emulate behaviors of fundamental particles found in nature. With this new perspective, we could potentially revolutionize a huge array of fields. Think about designing drugs that were once thought impossible, creating cutting-edge materials, or even accurately modeling incredibly complex phenomena like climate change. So what really sets these quantum chips apart from the ones we use in our everyday devices? To illustrate, consider my smartphone. It's far more powerful than the computer responsible for landing astronauts on the moon, but in essence, both devices share core similarities. The architecture of my smartphone and the Apollo computer relies on transistors that communicate in 2 states, off or on, 0 or 1. Through the years, we've successfully shrunk our devices to fit more and more transistors. Just to give you an idea of the progress we've made, a single human hair can accommodate around 15,000 transistors like those in my smartphone. However, quantum chips are built on a radically different foundation, the qubit. A qubit isn't just a simple switch that can be either on or off. Instead, it can be in a state where it's both on and off at the same time, thanks to a phenomenon known as superposition. Imagine flipping a coin. A conventional bit is like flipping it and checking whether it lands on heads or tails. A qubit, however, is like spinning the coin. While it's in motion, it represents both heads and tails until it settles. And there's more. Qubits can interact with each other through something called quantum entanglement. When you combine multiple qubits, the result is exponentially greater than simply adding bits. This allows for information processing that's incredibly efficient. If this sounds mind-bending, that's completely normal. It challenges the way we think because our brains are wired to understand the tangible world around us. To make it more relatable, think of navigating a maze. A bit is like a solitary explorer trying different paths one by one to find the exit. It will eventually succeed, but the complexity of the maze affects how long it takes. A qubit, on the other hand, is like an explorer that can traverse every single path in the maze simultaneously, thanks to that magical superposition. Now, let's pause for a moment and consider the origins of this groundbreaking idea. When did people start working on quantum computing? The whole concept began to take shape in the early 1980s. Pioneers like Paul Ben and the famous physicist Richard Feynman reached a similar conclusion. Traditional computers based on bits would never be able to simulate quantum phenomena effectively. In 1985, David Deutsch introduced the concept of a universal quantum computer capable of simulating any physical system and executing quantum algorithms. Early progress primarily happened in the realms of mathematics and algorithms. In the 1990s, mathematician Peter Shor developed a quantum factoring algorithm. To put that in plain English, he showed that a quantum computer could decrypt complex cryptographic keys. The first prototype of a quantum computer emerged from MIT in 1998. Still, significant advances were slow until companies and governments began investing seriously. IBM and Google are notable players in this field, as are governments like China, which has been heavily investing in quantum technology. In 2019, Google managed to create a 53-qubit machine known as Sycamore. Then, in 2022, IBM raised the stakes with their Osprey, which utilizes 433 qubits. And hold on to your hats. By December 2024, China Telecom is set to introduce Tianwen 504, boasting the most qubits in a quantum computer yet. Now, here's where things get tricky. Why has it taken such a long time to develop this technology? Remember the coin example I mentioned? The challenge lies in maintaining qubits in a constant state of superposition, the coin being both heads and tails simultaneously, for a significant amount of time. Achieving this is almost impossible, and that's what drives the complex design of these machines. The cooling systems you see are meant to keep the chips at an astonishing temperature of -273 degrees Celsius. Yes, these chips are huge fans of the cold. These quantum computers are housed in vacuum chambers to minimize any environmental interference. A tangled web of wiring transmits information at various temperatures, a captivating visual, like a cascade of cables. Yet, despite their intricate architecture, these machines are not yet competitive with supercomputers. They still suffer from a high error rate, making their use predominantly experimental. So how far away are we from practical use of quantum computers? That's the million-dollar question. Currently, quantum computing is still in the stage of overcoming a series of difficulties. First and foremost, it's incredibly challenging to maintain qubits in their desired states. The analogy here? Picture the quantum state of a qubit being like a drunk person. Sometimes they can act sober and produce useful data, but other times, not so much. Now, when traditional computers encounter errors, we hardly notice it because their architecture is solid, equipped with highly effective error correction systems. For quantum computers, however, correcting errors requires a large number of additional qubits. Here lies another challenge. While adding qubits to a quantum computer theoretically enhances capability, it also amplifies the potential for errors. The final major hurdle? Scalability. Constructing a quantum computer with enough qubits to tackle real-world problems is incredibly complex. The current systems have a limited number of qubits. Even the 504 qubits of the Chinese Kang remain far below the million qubits that would be necessary to solve complex problems on a grand scale. At this point, you might be thinking, this doesn't sound as close as we're led to believe. You're right. That's precisely why I approach discussions on quantum computing with caution. But Willow, Google's quantum chip, marks a significant step forward. What makes Willow special is that it has improved the qubit coherence time, what I like to call the sober time of the system, by 5-fold. This means that Google's engineers have managed to keep the computer stable for longer periods without making errors, which opens doorways to more productivity. Not only that, with increased coherence time, the system can rapidly reconfigure qubits that temporarily lose their desired state. In simpler terms, it means this machine will remain in its quantum state and self-correct much more reliably. That's a big breakthrough. However, it's important to remember that these machines will likely remain experimental for a few more years. Yes, some companies are utilizing these systems in the cloud, but currently, their applications are limited primarily to medical research, and results are still modest. So, when will quantum computers be truly useful? The prize for achieving this is extraordinarily valuable. As we will see, the first ones to succeed will wield a powerful tool capable of disrupting the global financial system, among other things. Governments are pushing research in this area, and China is leading the charge, investing $15 billion in the last 5 years, followed by the European Union with half that amount. Now, let's talk about the timeline. Experts suggest that quantum computing will pass through 3 stages. Until 2030, it will continue to produce many errors, and we'll see only limited commercial applications. The significant impact is expected between 2030 and 2040, when these systems start to gain a substantial advantage over traditional computers in areas like logistics, financial modeling, and pharmaceutical research. At this point, you might be wondering what I'll look like when we finally reach that stage. I can only imagine that by then, quantum computers will be capable of handling complex, large-scale problems. But I don't know about you. I see this quantum dream as a distant chimera. On one hand, it's exciting to think about solving significant global challenges, but considering the risks involved and the power this technology would grant to those who control it, it can be a bit daunting. Because here's the deal. The race for quantum computing has a rather dangerous edge. Let's circle back to Peter Shor, our friend who developed the quantum factoring algorithm. This algorithm provides a roadmap for quantum computers to decode the cryptographic keys we use to safeguard our wealth, our personal health information, and confidential communications. Current security systems are based on complicated mathematical formulas that leverage prime numbers, making it nearly impossible to decrypt them without knowing the original factors. For instance, multiplying 23 and 29 gets you 667, but figuring out what those prime numbers were without prior knowledge is extremely tough. This is precisely what we call factoring. Our financial systems, digital signatures, and cryptocurrency protocols depend on this hard-to-crack math, and you might be thinking, are our security systems at risk? At the moment, fortunately, not yet. To compromise something like Bitcoin, you would need an astonishing number of qubits, somewhere in the range of 1 to 13 million, with error-correcting abilities. Right now, Willow has only 105 qubits, so we're still a long way off from that reality. However, that doesn't mean we're sitting still. Researchers are already working on new cryptographic systems, such as quantum key distribution, or QKD. Just a little preview of what's to come. QKD utilizes individual photons to generate secret codes transmitted through fiber optics. The best part? Thanks to a principle in quantum physics that states observing a photon changes its quantum state, any attempt to intercept that code will render it useless. How cool is that? If you want to keep up with all of these exciting developments and stay informed, be sure to subscribe to AI Thunder. We're dedicated to bringing you the latest and greatest in AI and technology news so you won't miss a beat. As we wrap up, let's take a moment to think about the future. Quantum computing holds tremendous promise while also presenting risks that we cannot ignore. Astounding breakthroughs like Google's Willow may pave the way towards solving complex problems that have stumped humanity, but the power dynamics it introduces could reshape our world. So let's stay curious, stay informed, and most importantly, stay safe as we navigate this fascinating, ever-evolving landscape of quantum technology. Thanks for joining me today, and I'm looking forward to catching you in our next episode here at AI Thunder. Until then, stay tuned for more electrifying updates and intriguing discussions.